ये है मैकेनिकल प्रॉपर्टी ऑफ द फ्लूइड्स। तो इसमें पहले इसका देख लेते हैं PYQ और फिर इसका देखेंगे NCERT। तो NCERT तो इसमें से शायद नहीं आते हैं, फिर भी देख लेंगे इसका क्विकली। तो बैरोमीटर इज कंस्ट्रक्टेड using a liquid density of 5 kg per meter cube. But put the height of the liquid column when the mercury barometer reads 76 cm, डेंसिटी ऑफ द मर्करी जो है 13,600 kg पर क्यू दिया हुआ है। तो डेंसिटी ऑफ लिक्विड रोयल इक्वल टू 508 kg पर मीटर क्यूब, डेंसिटी ऑफ मर्करी रोयल इक्वल टू 13,600 kg पर मीटर क्यूब, और बैरोमीटर का हाइट दिया हुआ 76 सेंटीमीटर यानी 0.16 मीटर। तो रो लिक्विड इक्वल टू रो मर्करी यानी H रो G इक्वल टू HM रो G। तो यहाँ से HL इक्वल टू कितना आ जाएगा 13.6 मीटर। तो इसका आंसर कितना जाएगा 13.6 मीटर, ऑप्शन बी। फिर आता है कि you tube as shown in the figure, barter and the oil are in the left side and the right side of the tube respectively. The height from the bottom for barter and the oil columns are 15 cm and 20 cm respectively. The density of the oil कितना हो जाएगा, take rho equal to 1000 kg per meter cube। तो यहाँ पर दिया 15 सेंटीमीटर या 20 सेंटीमीटर बाटर, इधर ओल दिया हुआ है। तो अकॉर्डिंग टू द पास्कल लॉ, pressure applied to an enclosed fluid is transmitted undiminished to the every point of the fluid and the walls of the containing vessel। तो इन द गिवन सिचुएशन एज फॉर इन द फ्लैंक फिगर इधर 15 सेंटीमीटर हो गया, इधर 20 सेंटीमीटर हो गया। तो प्रेफर ड्यू टू द वाटर कॉलम ऑफ द हाइट 15 सेंटीमीटर इक्वल टू प्रेफर ड्यू टू द होल कॉलम ऑफ द हाइट 20 सेंटीमीटर, यानी कि HW रो WG इक्वल टू H0 रो नॉट G। तो रो नॉट इक्वल टू आ जाएगा कितना 15/20 रो नॉट। तो रो नॉट इक्वल टू आ जाएगा 15/20 गुना 1000 यानी 750 kg पर मीटर क्यूब। तो यहाँ से आंसर कितना आ जाएगा, इसका आंसर आएगा ऑप्शन बी 750 kg पर मीटर क्यूब। नेक्स्ट है a U-tube with both ends open to the atmosphere is partially filled with water. Oil which is immeasurable with the water is poured into one side until it stands at a distance of 10 mm above the water level on the other side. Meanwhile, the water rises by 55 mm from its original level. The density of the oil कितना हो जाएगा, तो यहाँ पर oil दिया हुआ है, इधर दिया हुआ है वाटर, ये हो गया 55 mm फिर 55 mm इनिशियल वाटर लेवल, फिर फाइनल वाटर लेवल 10 mm इधर दिया हुआ है। तो इसमें है कि प्रेशर ऑफ द टू पॉइंट्स लाई इन द सेम हॉरिजॉन्टल level should be equal to same and H is equal to P is equal to HDG. Both ends of the U-tube are open, so the pressure on the both the free surface must be equal. तो P1 equal to P2 यानी H oil F oil G is equal to H बटे F बटे G। तो F oil कितना हो जाएगा, स्पेसिफिक डेंसिटी ऑफ द oil। तो F oil हो जाएगा H बटे इंटू F बटे बाई G इंटू H oil बाई G। तो आ जाएगा 928 kg पर मीटर क्यूब। तो इसका आंसर कितना आ जाएगा, इसका आंसर आएगा ऑप्शन डी 928 kg पर मीटर क्यूब। नेक्स्ट है कि टू नॉन मिक्सिंग लिक्विड ऑफ द डेंसिटी रो एंड एन, जहाँ एन रो जहाँ एन इज ग्रेटर देन 1 है, आर पुट इन द कंटेनर। द हाइट ऑफ द ईच लिक्विड इज एच, ए सॉलिड फ्लूइड ऑफ लेंथ एल एंड डेंसिटी डी इज पुट इन दिस कंटेनर। द सिलेंडर फ्लोट्स विद एक्सिस वर्टिकल एंड द लेंथ रो एल, जहाँ रो जो है लेस देन 1 है, इन द डेंस लिक्विड द डेंसिटी डी इज इक्वल टू कितना हो जाएगा। तो अकॉर्डिंग टू द क्वेश्चन द सिचुएशन कैन बी ड्रॉन बाय द फॉलोइंग। तो यहाँ रोल है 1 माइनस रोल हो गया और डी हो गया, ए हो गया, फिर रो हो गया। अकॉर्डिंग अप्लाइंग द आर्किमिडीज प्रिंसिपल, वेट ऑफ द सिलेंडर इज इक्वल टू अप थ्रस्ट प्लस 1 प्लस अप थ्रस्ट 2, यानी कि AL DG इक्वल टू 1 माइनस P AL रो जी प्लस रो एल ए एन रो जी। तो D इज इक्वल टू एन 1 माइनस P इंटू रो और P एन रो। तो P माइनस रो माइनस P रो प्लस एन P रो इज इक्वल टू कितना आ जाएगा, रो 1 प्लस एन माइनस 1 रो। तो इसका आंसर कितना आ जाएगा, इसका आंसर आएगा ऑप्शन सी 1 प्लस एन माइनस 1 रो इन P इंटू रो आ जाएगा। फिर आता है the approximate depth of an ocean is 2700 meter. The capacity of the water is 45.4 गुना 10⁻11 per pascal and the density of the water is 10/3 kg per meter cube. But fractional compression of the water will be obtained at the bottom of the ocean. The given d equal to 2700 meter, rho equal to 10⁻3 kg per meter cube और कंप्रेसिविटी हो जाता है 45.4 गुना 10⁻11 पर पास्कल। द प्रेशर ऑफ द बॉटम ऑफ द ओशियन इज गिवन बाय P इक्वल टू रो GD यानी 27 गुना 10⁻6 पास्कल। अब यहाँ से निकालेंगे तो फ्रैक्शनल कंप्रेशन आ जाएगा कंप्रेसिविटी इंटू प्रेशर, तो आ जाएगा 1.2 गुना 10⁻²। तो इसका आंसर कितना आ जाएगा, इसका आंसर आएगा ऑप्शन सी 1.2 गुना 10⁻²। फिर आता है कि the velocity of a small ball of the mass m and density d when dropped in a container filled with the glycerin becomes constant after some time. If the density of the glycerin is d/2 then the viscous force acting on the ball कितना हो जाएगा। तो हम जानते हैं कि the mass of the ball of small ball is m, density of the glycerin is d/2, viscous force equal to weight minus buoyant force होता है, यानी कि viscous force हो जाएगा v d1g minus v d2g और d1 इक्वल टू हो जाएगा d, d2 इक्वल टू हो जाएगा d/2। Substituting the given value in the viscous force expression, we get viscous force equal to Vdg minus Vdy2 into g। viscous force हो जाएगा Vdg/2 यानी कि mg/2। तो यहाँ से कितना आएगा आंसर, आंसर आएगा ऑप्शन है mg/2। अगला है Two small spherical metal balls having the equal masses are made from the materials of the density ρ1 and the ρ2, जहाँ ρ1 is equal to हो गया 8 ρ2, have radii 1 mm and 2 mm respectively. They are made to fall vertically from the raft in the viscous medium whose coefficient of the viscosity equals eta and whose density is 0.1 ρ2. The ratio of their terminal velocity would be. Next है two small spherical metal balls having the equal masses are made from the material of density ρ1 and the ρ2, जहाँ ρ1 is equal to 8 ρ2 and have radii of the 1 mm and 2 mm respectively. They are made to fall vertically from the raft in the viscous medium whose coefficient of viscosity equals n eta and whose density is equal to 0.1 rho 2. The ratio of the terminal velocity कितना हो जाएगा, तो the terminal velocity achieved by ball is viscous in a viscous fluid given by Vt is equal to 2 rho minus sigma r square g by 9 eta, में रो जो है डेंसिटी ऑफ द मेटल ऑफ द बॉल है, ईटा जो है सिग्मा जो है डेंसिटी ऑफ द विस्कस मीडियम है और ईटा जो है कोफिशिएंट ऑफ द विस्कोसिटी ऑफ द मीडियम है. तो Vt इक्वल टू रो 1 माइनस सिग्मा आर 1 का स्क्वायर इंटू जी बाई 9 ईटा, यानी 8 रो 2 माइनस सिग्मा आर 1 का स्क्वायर बाई जी बाई 9 ईटा. अब यहाँ से करें तो सिमिलरली फॉर द सेकंड बॉल Vt2 इक्वल टू 2 रो 2 माइनस सिग्मा आर 2 का स्क्वायर जी बाई 9 ईटा. तो दोनों को डिवाइड कर दें तो Vt1 बाई Vt2 आ जाएगा 29/36. तो इसका आंसर कितना जाएगा, ऑप्शन डी 29/36. फिर आता है कि स्मॉल होल of the area of the cross section 2 mm square is present near the bottom of a fully filled open tank of the height 2 meter. Take g equal to 10 meter per second का the rate of the flow of the water through the open hole will be nearly, तो the rate of the liquid flow moving with the velocity v through an area a is given by r rate is equal to area into velocity. तो a दिया हुआ 2 mm का स्क्वायर यानी 2 × 10⁻⁶ मीटर स्क्वायर, हाइट ऑफ द टैंक दिया हुआ 2 मीटर. तो द गिवन सिचुएशन कैन आल्सो डिपिक्टेड एज शोन इन द फिगर. तो ये यहाँ पर 2 mm का स्क्वायर एट द वेलोसिटी ऑफ द लिक्विड फ्लो इज गिवन एज v इक्वल टू √2gh. तो r इक्वल टू a v इक्वल टू a √2gh. सब्स्टिट्यूटिंग द गिवन वैल्यू वी गेट r इक्वल टू 2 × 10⁻⁶ √2 2 × 10⁻2, तो कितना आ जाएगा 12.6 × 10⁻⁶ मीटर क्यूब पर सेकंड. तो आंसर आएगा ऑप्शन डी 12.6 × 10⁻⁶ मीटर क्यूब पर सेकंड. फिर इसके बाद आता है कि a small sphere of the radius r falls from the raft in the viscous fluid. As a result, heat is produced due to the viscous force. The rate of the production of the heat when the sphere attains its terminal velocity is proportional to the rate of heat produced. dq by dt होता है f गुना vt. तो f is the viscous force, vt is the terminal velocity. तो f equal to 6 pi eta r vt. तो dq by dt equal to होता है 6 pi eta r vt गुना vt, यानी 6 pi eta r vt का स्क्वायर. तो vt equal to हो जाएगा 2/9 r स्क्वायर सिग्मा रो माइनस सिग्मा बाई ईटा इंटू जी. तो vt इक्वल टू होता है डायरेक्टली प्रोपोर्शनल टू आर स्क्वायर. तो dq बाई dt डायरेक्टली प्रोपोर्शनल टू आर इंटू आर स्क्वायर का स्क्वायर, यानी आर के पावर हो जाएगा 5. तो आंसर आएगा ऑप्शन ए आर के पावर 5. फिर आता है बेंड विद द स्पीड ऑफ द 40 मीटर पर सेकंड ब्लोज पैरेलल टू द रूफ ऑफ ए हाउस. द एरिया ऑफ द रूफ इज 250 मीटर स्क्वायर. एज्यूमिंग दैट द प्रेशर इनसाइड द हाउस इज एटमॉस्फेरिक प्रेशर. द फोर्स एक्सर्टेड बाय द विंड ऑन द रूफ एंड द डायरेक्शंस ऑफ द फोर्स कितना हो जाएगा, तो रो एयर दिया 1.2 kg पर मीटर क्यूब. तो फ्रॉम द बर्नौली थ्योरम P1 plus half rho P1 के square is equal to P2 plus half rho V2 के square, where P1 and the P2 are the pressure inside and outside the roof, and V1 and V2 are the velocity of the wind inside and outside the roof. Neglect the width of the roof, तो P1 minus P2 equal to half rho P2 minus V1 के square, यानी 960 न्यूटन पर मीटर स्क्वायर. और F is equal to P1 minus P2 into A, यानी 960 गुना 250, यानी 2.4 गुना 10⁻5 न्यूटन. तो either pressure inside the roof is more than the outside to it, so the force will act in the upward direction. तो इस आ जाएगा 2.4 गुना 10⁻5 न्यूटन ऑफ बार्ट्स. तो इसका आंसर कितना जाएगा, ऑप्शन सी 2.4 गुना 10⁻5 न्यूटन ऑफ बार्ट्स. फिर आता है कि द सिलिंड्रिकल ट्यूब ऑफ द स्प्रे पंप हैज द रेडियस r, one end of the which has the n fine holes, each of the liquid radius r. If the speed of the liquid in the tube is v, the speed of the ejection of the liquid through the hole कितना हो जाएगा. तो इसमें से अगर निकालेंगे तो अकॉर्डिंग टू द इक्वेशन ऑफ द कंटिन्यूटी a v इक्वल टू होता है कांस्टेंट, a इज सिलिंड्रिकल ट्यूब एंड v इज द वेलोसिटी ऑफ द लिक्विड इन दैट ट्यूब. तो वॉल्यूम इन द फ्लो रेट होता है वॉल्यूम इन आउट ऑफ द फ्लो रेट. तो पाई आर स्क्वायर इंटू वी इक्वल टू एन पाई आर स्क्वायर इंटू वी डेफ. तो वी डेफ इक्वल टू हो जाएगा आर स्क्वायर वी बाई एन आर स्क्वायर. तो द स्पीड ऑफ द इजेक्शन ऑफ द लिक्विड थ्रू द होल आ जाएगा आर स्क्वायर वी बाई एन आर के स्क्वायर. तो इसका आंसर कितना जाएगा, इसका आंसर आएगा ऑप्शन बी वी आर स्क्वायर बाई एन आर स्क्वायर आ जाएगा. नेक्स्ट है कि ए लिक्विड दे नॉट बेट द सॉलिड सरफेस इफ द एंगल ऑफ द कॉन्टैक्ट. तो आंसर आएगा ऑप्शन सी ग्रेटर दैन द 90 डिग्री. तो एक लिक्विड डाई नॉट बेट द सॉलिड सरफेस इफ द एंगल ऑफ द कॉन्टैक्ट इज ऑब्ट्यूज, दैट मीन्स ग्रेटर दैन 90 डिग्री हो जाता है. फिर आता है एक कैपिलरी tube of the radius r immersed in the water and water as it into in it to a height of the h. The mass of the water in the capillary tube is 5 gram. Another capability of radius of 2r is morphine the butter. The mass of the butter will large in active कितना हो जाएगा, तो h इक्वल टू f cos थीटा बाई रो जी आर होता है, तो h इनवर्सली प्रोपोर्शनल टू r हो जाएगा, तो h2 h1 बाई h2 हो जाएगा 2, तो m इक्वल टू होता है a h रो, तो m2 बाई m1 हो जाएगा 1/2, तो m2 इक्वल टू कितना हो जाएगा 2.5 ग्राम, तो इसका आंसर कितना हो जाएगा ऑप्शन डी 2.5 ग्राम। फिर आता है कि soap bubble having a radius of the 1 mm is blown from a detergent solution having a surface tension of 2.5 on the form of 2 Newton per meter. The pressure inside the bubble equals at a point G0 below the free surface of the water in a container. Taking G equal to 10 meter per second square, density of the body equal to 10 kg per meter cube, the value of the G0 कितना हो जाएगा, तो the excess pressure inside the soap bubble of the radius are given by P equal to 40 by R, जहाँ T जो है surface tension है. If P naught be the outside pressure from the water, then the total pressure inside the bubble becomes P1 equal to P naught plus 40 by R. The pressure at the depth Z0 below the water surface, P2 equal to P0 plus Z0 rho g. As it is given that the pressure inside the bubble is same as the pressure at the depth Z0, then the equation 1 and 2 beget P0 plus 40 by R equal to P0 plus Z0 rho g. तो Z0 equal to 40 by R rho g. यहाँ पे Z0 कितना आ रहा है 1 सेंटीमीटर, तो इसका आंसर होगा ऑप्शन बी 1 सेंटीमीटर। फिर है कि ए रेक्टेंगुलर फिल्म ऑफ द लिक्विड एक्सटेंड फ्रॉम द 4 सेंटीमीटर गुना 2 सेंटीमीटर टू 5 सेंटीमीटर गुना 4 सेंटीमीटर। इफ द वर्क डन इज 3 गुना 4 माइनस 4 जूल, द वैल्यू ऑफ द सरफेस टेंशन ऑफ द लिक्विड कितना हो जाएगा, तो हम जानते हैं कि इंक्रीज इन द सरफेस एनर्जी होता है वर्क डन इन द एरिया गुना सरफेस टेंशन, यानी इंक्रीज इन द सरफेस एरिया होता है डेल्टा इज इक्वल टू 5 गुना 4 माइनस 4 गुना 2 फिल्म 2 सरफेस होता है, तो 20 माइनस 8 गुना 2 इक्वल टू 24 सेंटीमीटर स्क्वायर, तो 24 गुना 10 को माइनस 4 मीटर स्क्वायर। तो वर्क डन डब्ल्यू इक्वल टू टी डॉट डेल्टा है, तो यहाँ पर टी इक्वल टू आएगा 1/8 यानी 0.125 न्यूटन पर मीटर, तो इसका आंसर आएगा ऑप्शन बी 0.125 न्यूटन पर मीटर। फिर आता है 3 liquids of density ρ1, ρ2 and ρ3 with ρ1 greater than ρ2 greater than ρ3 have the same value of the surface tension T rise to the same height in the 3 identical capillary. The angle of the contact θ1, θ2, θ3 obey the according to the afferent formula of the capillary tube, H is equal to 2T cos theta by rho gr, cos θ1 by ρ1 is equal to cos θ2 by ρ2 is equal to cos θ3 by ρ3। अब यहाँ से अगर निकालें तो cos थीटा जो होता है डायरेक्टली प्रोपोर्शनल टू रो है, तो ρ1 इक्वल टू सबसे बड़ा होगा, फिर ρ2 फिर ρ3, तो cos θ1 सबसे बड़ा होगा, फिर cos θ2 फिर cos θ3, तो एंगल उल्टा हो जाएगा, तो जीरो से सबसे बड़ा हो जाएगा π/2, जीरो θ1 जो होता है जीरो के इक्वल भी हो सकता है लेकिन बड़ा भी होगा, तो θ3 फिर θ2 फिर θ1, तो आंसर कितना जाएगा, आंसर आएगा ऑप्शन बी कि π/2 θ3 θ2 θ1 और इक्वल टू जीरो और ग्रेटर देन जीरो भी हो सकता है। फिर आता है a certain number of the spherical drops of the liquid of the radius r collide to form a single drop of the radius r and volume v. If T is the surface tension of the liquid, then the energy lead A final minus initial into T, तो A is equal to 4 pi r square यानी 3/3 4 pi r cube by r यानी 3 v by r, तो A T is equal to 4 pi r square यानी v by 4/3 pi r cube into 4 pi r square यानी 3 v by r, तो एनर्जी लीड 3v2 इक्वल टू 1 by r minus 1 by कैपिटल R, तो एनर्जी हो जाएगा ऑप्शन सी की एनर्जी रिलीज हो जाएगा 3v2 1 माइनस स्मॉल r by 1 माइनस कैपिटल R। फिर है कि द वेटेबिलिटी ऑफ ए सरफेस बाय ए लिक्विड डिपेंड्स प्राइमली ऑन द आंसर है ऑप्शन डी सरफेस एंगल ऑफ द कॉन्टैक्ट बिटवीन द सरफेस एंड द लिक्विड पर डिपेंड करता है। द वेटेबिलिटी ऑफ द सरफेस बाय ए लिक्विड डिपेंड्स प्राइमली ऑन एंगल ऑफ कॉन्टैक्ट बिटवीन द सरफेस एंड द लिक्विड। और यहाँ पर दिया हुआ है मैकेनिकल प्रॉपर्टी ऑफ द फ्लूइड का एनसीईआरटी, तो एनसीईआरटी से तो कुछ भी नहीं आया है लेकिन फिर भी क्विकली इसको देख लेते हैं। तो इसमें है कि इन दिस चैप्टर बी फॉलो स्टडी फ्रॉम कॉमन फिजिकल प्रॉपर्टी ऑफ द लिक्विड एंड गैसेज। लिक्विड एंड गैसेज कैन फ्लो एंड देयरफॉर कॉल्ड फ्लूइड्स। It is this property that distinguishes a liquid and gases from the solid in a basic way. Fluids are everywhere around us. Earth has an envelope of air and 2/3 of its surface is covered with the water. Water is not only necessary for our existence. Every mammalian body constitutes mostly of the water. All the processes occurring in the living beings, including plant, are mediated by the fluid. Thus, understanding the behavior and the property of the fluid is important. However, fluids different from the solids. What is common in the liquid and the gases? Unlike a solid, a fluid has no definite shape of its own. Solids and liquids have a fixed volume, whereas a gas fills the entire volume of its container. We have learned in the previous chapter that the volume of the solid can be arranged changed by the stress. The volume of the solid, liquid, or gas depends upon the stress or the pressure acting on it. When we talk about the fixed volume of the solid or the liquid, we mean its volume under atmospheric pressure. The difference between the gas phase and the solid for the liquid is that for the solid or the liquid there, the change in the volume due to the change of the external pressure is rather small. In other words, solids and liquids have much lower compressibility as compared to the gas phase. Sphere of stress can change in the shape of the solid keeping its volume fixed. The key product of the fluid is that they offer very little resistance to the sphere of stress. Their shape changes by the application of very small sphere of stress. The shearing strength of the fluid is about a million times smaller than that of the solid. फिर आता है prefer. तो a sharp needle when pressed against our skin pierces it. Our skin, however, remains intact when a blunt object with a wider contact area, say the back of a spoon, is pressed against it with the same force. If an elephant were to step on a man's chest, his ribs would crack. A circus performer across whose chest a large, light but strong wooden plank is puffed is severed from the precedent. Such everyday experience convinces us that both the forces and the area coverage area are important. A smaller the area on which the force acts, greater is the impact this impact in another prefer. When an object is submerged in a fluid at the depth, the fluid exerts a pressure force on the surface. This force is always normal to the object's surface. This is so because if there were a component of the force parallel to the surface, the object will also exert a force on the fluid parallel to it. As a consequence of the Newton's third law, this force will cause the fluid to flow parallel to the surface. Since the fluid is at rest, this cannot happen. Hence, the force exerted by the fluid at rest has to be perpendicular to the surface in contact with it. Rather, the normal force exerted by the fluid at a point may be measured, and a light form of one such prefer measuring device is shown. It consists of a vacated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed at a point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring and force and is thereby measured. फिर यहाँ पर दिया हुआ है the force exerted by the liquid in the breaker on the submerged object or on the walls is normal perpendicular to the surface at all points. And add a light device for measuring a prefer ये दिखाया हुआ है. फिर आता है if F is the magnitude of this normal force on the piston of area A, then the average force P average is defined as the normal force acting per unit area. तो P average equal to होता है F by A. FTP means standard temperature 0 degree Celsius and 1 atm pressure. फिर उसके बाद आता है कि in principle the piston area can be made arbitrarily small. The pressure is then defined in the limiting sense as P जो होता है limit delta A tends to 0 delta F by delta A. Pressure is a scalar quantity. Be reminded that it is the component of the force normal to the area under the concentration and not the vector force that appears in the numerator. Its dimensions are m L1 minus 1 T minus 2. The SI unit of the pressure is Newton meter square. It has been named as the Pascal in honor of the who carry out binary studying of fluid pressure. A common unit of pressure is the atmosphere. That means the pressure exerted by the atmosphere at the sea level. One atmosphere is equal to 1.013 another for 5 Pascal. Another quantity that is indispensable in the describing fluid is the density rho. For a fluid of the mass m occupying volume v, rho is equal to m by v. The dimensions of the density are the ml minus 3. Its SI unit is the kg per meter cube. It is a positive scalar quantity. A liquid is largely incompressible, and its density is therefore nearly constant at all pressure. Gases, on the other hand, exhibit a large variation in the density with the pressure. The density of the water at 4 degrees Celsius, 245 Kelvin, is 1 3 kg per meter cube. The relative density of the substance is the ratio of the density to the density of the water at 4 degrees Celsius. It is a dimensionless positive scalar quantity. For example, the relative density of the aluminum is 2.7. If density is 2.7 3 kg per meter cube, the density of the some common fluid are displayed in the table 9.1. फिर आता है क्वेश्चन दिया हुआ है कि the two thigh bones femur each of the cross section area 10 cm square support the upper part of the human body mass 40 kg. Estimate the average pressure estimated by the femurs. तो इसमें है कि the total cross sectional area of the femur is a गुना the a is equal to 2 गुना 10 power 10 cm square यानी 20 गुना 10 power minus 4 meter square. The force acting on them F equal to 40 kg gram weight यानी 400 Newton. The G equal to 10 meter per second square. This force is acting vertically down and hence normally on the femur. Thus the average pressure is P average is equal to F by N into 2 power 5 Newton meter square. फिर आता है Pascal law. तो the observed that the pressure in a fluid at rest is the same at all points if they are at the same height. This fact may be demonstrated in a simple way. Proof of the Pascal law ABCD F is an element of the interior of a fluid at rest. This element in the form of a right-handed angular prism. The element is small so that the effect of the gravity can be ignored, but it has been enlarged for the sake of the clarity. Figure 9.2 shows an element in the interior of a fluid at rest. This element ABCDF is the form of the right angular prism. In principle, this prismatic element is very small so that every part of it can be considered at the same depth from the liquid surface, and therefore the effect of the gravity is the same at all these points. But for the clarity we have enlarged this element. The force on this element are those exerted by the rest of the fluid, and they must be normal to the surface of the element as discussed above. Thus the fluid exerts a pressure PA, PB and the PC on the element of the area corresponding to the normal force FA, FB and the FCF shown in figure 9.2 on the face BEFC, ADFC and the ADEB noted by the AA, AB, AC respectively. Then the FB sin theta is equal to FC, FB cos theta is equal to FA, AB sin theta is equal to FC, and the AB cos theta is equal to AA. So FB by AB is equal to FC by FA equal to FA by AB. So PA is equal to PC is equal to PA. Hence, pressure exerted is the same in all the directions in the fluid at rest. It again reminds us that like other types of the stress, pressure is not a vector quantity. No direction can be assigned to it. The force against any area between or bonding is a fluid at rest, and the pressure is normal to the sea, regardless of the orientation of the area. Now consider a fluid element in the form of a horizontal bar of the uniform cross-section. The bar is in equilibrium. The horizontal force exerted on its two ends must be balanced, or the pressure at the two ends should be equal. This proves that for the liquid in equilibrium, the pressure is the same at all points in the horizontal plane. Suppose the pressure were not equal in the different parts of the fluid, then there would be a flow, and the fluid will have some net force acting on it. Hence, in the absence of the flow, the pressure in the fluid must be same everywhere in the horizontal plane. फिर आता है variations of the pressure with the depth. To consider a fluid at a rest in the container. In figure 9.3, point A is at a height h, a point 2. The pressure at the point 1 and 2 are the P1 and the P2 respectively. Consider a cylindrical element of the fluid having area of the base A and the height h. As the fluid is at rest, the resultant horizontal forces should be 0 and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical direction are due to the fluid pressure at the top P1A acting downward, at the bottom P2A acting upward. If mg is the weight of the fluid in the cylinder, we have P2 minus P1 into A is equal to mg. If now rho is the mass density of the fluid, we have the mass of the fluid to be m is equal to rho v यानी rho ha into A. So that P2 minus P1 is equal to rho gh. तो यहाँ पर दिया हुआ है fluid under gravity. The effect of the gravity is illustrated through the pressure on a vertical cylindrical column. फिर आता है pressure difference depends on the vertical distance h between the points 1 and 2, mass density of the liquid rho, and the acceleration due to gravity g. If the point 1 under the discussion is shifted to the top of the fluid, say water, which is open to the atmosphere P1, may be replaced by the atmospheric pressure PA, and we get the P2 by the P. Then the equation P is equal to PA plus rho GH. Thus the pressure P at the depth below the surface of the liquid open to the atmosphere is greater than the atmospheric pressure by an amount rho GH. The excess of the pressure P minus PA at the depth is called the gauge pressure at that point. The area of the cylinder is not appearing in the expression of the fluid pressure. Thus, the height of the fluid column is important, and not the cross section or the base area of the shape of the container. The fluid pressure is the same at all points at the same horizontal level, same depth. The reality appreciated though the example of the hydrostatic paradox. Consider three vessels A and B and C of the different shapes. They are connected at the bottom by a horizontal pipe. On filling with water, the level in the three vessels is the same, though they hold different amount of the water. This is so because water at the bottom has the same pressure below each section of the vessel. फिर यहाँ पर दिया हुआ illustration of the hydrostatic paradox. The three vessels A, B and C contain different amounts of the liquid all up to the same height. फिर आता है what is the pressure on the swimmer 10 meter below the surface of the lake. तो H इक्वल टू 10 मीटर, रो इक्वल टू 1000 kg पर मीटर टेक जी इक्वल टू 10 मीटर पर सेकंड स्क्वायर. तो P इक्वल टू पी ए प्लस रो जी एच यानी 1.01 गुना 5 पास्कल प्लस 1000 kg पर मीटर को गुना 10 तो आएगा 2 atm. देयर इज 100% increase in the pressure from the surface level at a depth of the 1 kilometer. The increase in the pressure is 4 atm. Submarines were designed to be withstand such enormous pressure. अगला क्वेश्चन है कि एटमॉस्फेरिक प्रेशर एंड द गॉज प्रेशर. तो द प्रेशर ऑफ द एटमॉस्फेयर एट एनी पॉइंट इज इक्वल टू द वेट ऑफ द कॉलम ऑफ द एयर ऑफ द यूनिट क्रॉस सेक्शन एरिया extending from that point or to the top of the atmosphere. At the sea level, it is 1.013 गुना 5 पास्कल यानी 1 atm. फिर उसका आता है कि डिवाइड फॉर द फर्स्ट टाइम ए मेथड फॉर मेजरिंग द एटमॉस्फेरिक प्रेशर. ए लॉन्ग ग्लास ट्यूब क्लोज एट वन एंड filled with the mercury heated into a trap of the mercury is shown below. This device is known as the mercury barometer. The space above the mercury column in the tube contains only mercury vapor, whose vapor is so small that it may be neglected. Thus, the pressure at the point A is equal to 0. The pressure inside the column at point B must be the same as the pressure at the point C, which is atmospheric pressure PA. So P is equal to rho GH, where rho is the density of the mercury and H is the height of the mercury column in the tube. फिर आता है in the experiment, it found that the mercury column in the barometer has a height of about 76 cm at the sea level, equivalent to the 1 atmosphere 1 atm. This can also be obtained using the value of the rho. A common way of stating pressure is in the terms of the centimeter or mm of the mercury. Hg, a pressure equivalent to the 1 mm is called a torr after torricelli. 1 torr is equal to 133 Pascal. The mm of the Hg and the torr are used in medicine and the physiology. In metrology, a common unit is the bar and the millibar. 1 bar is equal to the square 5 Pascal. An open tube manometer is useful instrument for measuring the pressure differences. It consists of a U-tube containing a suitable liquid, that means low density liquid such as the oil, for measuring the small pressure differences, and high density liquid such as the mercury for large pressure difference. One end of the tube is open to the atmosphere and the other end is connected to the system whose pressure we want to measure. The pressure P at A is equal to the pressure at a point B. Part B normally measure is the gauge pressure, which is PA minus PA given by the equation 9.8 and is proportional to the manometer height H. यहाँ पर दिया P इक्वल टू 0 और यहाँ पर दिया हुआ है द मर्करी बैरोमीटर का. फिर आता है यहाँ पर दिया हुआ है द ओपन ट्यूब मैनोमीटर और टू प्रेफर मेजरिंग डिवाइसेज है जो दिए हुए. Prefer the same at the same level on both sides of the U-tube containing a fluid. For liquid, the density very little with over wide range in the pressure and the temperature, and we can treat it safely as a constant for our present purpose. Gases, on the other hand, exhibit the large variation in the density with large change in the pressure and the temperature. Unlike gases, liquid are therefore largely treated as the incompressible. फिर एक क्वेश्चन है कि the density of the atmosphere at the sea level is 1.29 kg per meter cube. Assume that it does not change with the altitude. Then how high would the atmosphere extend? तो जानते हैं कि रो जी एच इक्वल टू होता है 1.29 गुना 9.8 गुना एच यानी 1.01 गुना 5 पास्कल. तो एच इक्वल टू कितना हो जाएगा 8 किलोमीटर. In reality, the density of the air decreases with the height, so that the value of G, the atmospheric cover, extends with decreasing pressure over the 4 km. We should also note that sea level atmospheric pressure is not always 40 mm of the Hg. A drop in the Hg level by the 10 mm or more is a sign of a approaching storm. अगला क्वेश्चन है कि एट द डेप्थ ऑफ द 1000 मीटर इन एन ओशियन what is the absolute pressure, what is the gauge pressure, but find the force acting on the window of the area 20 cm on 20 cm of a submarine at this depth, the interior of which is maintained by a sea level atmospheric pressure. The density of the sea water is 1.03 गुना 10 kg per meter cube and G इक्वल टू 10 मीटर पर सेकंड स्क्वायर. तो हेयर एच इक्वल टू दिया हुआ है 1000 मीटर, रो इक्वल टू 1.013 गुना 10 kg meter cube. तो फ्रॉम द फिगर एब्सोल्यूट P is equal to P plus rho GH, यानी कि 4 ATM. Gauge pressure is equal to P minus P is equal to rho GH is equal to rho G. The pressure outside the submarine is P is equal to P plus rho GH and the pressure inside it is PA. And so the net pressure acting on the window is gauge pressure P is equal to rho GH. So the area of the window A is equal to 0.04 meter square. The force acting on it is F is equal to PG into A. तो कितना आ जाएगा 4.1 गुना 5 न्यूटन. फिर आता है hydraulic machines. So it is now considered what happens when we change the pressure on a fluid contained in a vessel. Consider a horizontal cylinder with a piston and 3 vertical tubes at different points. The pressure in the horizontal cylinder is indicated by the height of the liquid column in the vertical tubes. It is necessarily the same in all. If we push the piston, the fluid level rises in all the tubes, again reaching the same level in each of them. This indicates that when the pressure on the cylinder by increased, it by distributed uniformly throughout. We can see whenever the external pressure applied on any part of the fluid contained in the vessel, it is transmitted undiminished and equally in all directions. This is another form of the Pascal law and it has many applications in daily life. A number of devices such as the hydraulic lift and the hydraulic brakes are based on the Pascal's law. In the device, fluids are used for transmitting pressure. In a hydraulic lift, as shown in the figure 9.6, two pistons are separated by the space plate with liquid. A piston of the small cross-section A1 is used to exert a force F1 directly on the liquid. The pressure P is equal to F1 by A1 is transmitted throughout the liquid to the larger cylinder attached with a larger piston of the area A2, which results in an upward force of the P into A2. Therefore, the piston is capable of supporting a large force, large weight of say a car or a truck placed on a platform. F2 is equal to PA2 and F1 A2 by A1. By changing the force at A1, the platform can be moved up or down. The applied force has been increased by a factor of A2 by A1 and this factor is the mechanical advantage of the device. The example below clarifies it. फिर यहाँ पर दिया हुआ है schematic diagram illustrating the principle behind the hydraulic lift, a device used to lift the heavy loads. Next है कि two strings of the different cross section without needles filled with the butter are connected with a tightly fitted rubber tube filled with the butter. Diameters of the tube, a smaller piston and a larger piston are 1 cm and 3 cm respectively. Find the force exerted at the larger piston when the force of the 10 Newton is applied to the smaller piston. If the smaller piston is pushed in the through the 6 cm, how does the larger piston move out? So F2 equal to the A2 by A1 यानी into F1 is equal to 19 Newton. Butter is considered to be perfectly incompressible. Volume covered by the movement of the small piston inward is equal to the volume movement outwards due to larger piston. तो L1 A1 equal to L2 A2. यहाँ पे करेंगे तो कितना आ रहा है 0.61 cm. Note atmospheric pressure is common on both piston and has ignored. फिर अगला क्वेश्चन है कि in a car lift compressed air exert a force F1 on a small piston having a radius of 5 cm. This pressure is transmitted to a second piston of the radius 15 cm. If the mass of the car to be lifted is therefore 50 kg, calculate F1 what is the pressure necessary to accomplish this task. So since the pressure is measured, since the pressure is transmitted throughout the liquid, F1 is equal to A1 by A2 into F2. The air pressure तो यहाँ जाएगा 1.5 into 5 Newton, 3 Newton. The force is equal to P equal to F1 by M1. 1.9 into 5 Pascal. This is almost double that of atmospheric pressure. फिर आता है hydraulic brakes in automobiles also work on the same principle. When you apply a little force on the metal pedal with our foot, the master piston moves inside the master cylinder and the pressure is transmitted through the brake wheel to act on the piston of a larger area. A large force acts on the piston and is pushed down, expanding on the brake shoe against the brake lining. In this way, a small force on the pedal produces a large retaining force on the wheel. The important message advantage of the system is that the pressure set by the pressing pedal is transmitted equally to all cylinders attached to the four wheels so that the braking part of on all the four wheels. अब इसके बाद फिर आता है स्ट्रीमलाइन फ्लो. तो कहता है कि so far we have studied the fluid at rest. Now study of the fluid in the motion known as the fluid dynamics. When the water tap is turned on slowly, the water moves smoothly initially but loses its smoothness when the speed of the outflow is increased. In studying the motion of the fluid, we focus on our attention on what is happening to the various fluid particles at the various points in the space at a particular time. The flow of the fluid is said to be steady if at any point the velocity of each passing fluid particle remains constant at time. This does not mean that the velocity at different points in the space is same. The velocity of a particular particle may change as it moves from the one point to another. That is, at some other point the particle may have a different velocity, but every other particle which passes the second point will have exactly as the previous particle that had just passed the that point. Each particle follows a smooth path, and the path of the particle do not cross each other. फिर आता है यहाँ पर दिया हुआ है the meaning of the streamline, a typical trajectory of the fluid particle, a region of the streamline flow दिया हुआ है. So the path taken by the fluid particle under a steady flow is called a streamline. It is defined as the curve whose tangent at any point in the direction of the fluid velocity at that point. Consider the path of the particle as shown in the figure 9.7a. The curve describes how a fluid particles move with time. The curve PQ is like a permanent map of the fluid map indicating how the fluid streams. No two streamlines can cross both. If they do, oncoming fluid particles can go either one way or the other and the fluid would not be steady. Hence, in the steady flow, the map of the flow is stationary in that time. How do we draw closely of specified streamlines? If we intend to show a streamline of every flowing particle, we would end up with a continuum of the line. अब इसका क्या कहता है कि consider planes perpendicular to the directions of the fluid flow at 3 points P, R and the Q. The planes spaces are so chosen that their boundary be determined by the same set of the streamlines. This means that the number of the fluid particles crossing the surface is indicated by the P, R and the Q is the same. If the area of the cross section at this point are AP, AR and the AQ and the speed of the fluid particles for the BP, BR and the BQ, then the mass of the fluid delta MP crosses at delta AP is the small interval of time, delta P is the rho P, AP, BP, delta P. Similarly, the mass of the fluid delta MR flowing out crossing at AR is the same small time interval of delta T is the rho R, AR, BR into delta T, and the mass of the fluid delta MQ is equal to rho Q, AQ, BQ into delta T crossing at the AQ. The mass of the fluid liquid flowing out of equals the mass flowing in and holds in all the cases. Therefore, rho P, AP, BP delta T is equal to rho R, AR, BR delta T and is equal to rho Q, AQ, BQ delta T. For flow of the incremental fluid, rho R is equal to rho P is equal to rho Q. Equation 9.9 refer to AP, BP is equal to AR, BR is equal to AQ, BQ, which is called the equations of the continuity, and it is a statement of the conservation of mass in the flow of the incompressible fluid. In general, AB is equal to constant. AB gives the volume of flux for the flow rate and even constant for the pipe of the flow. The narrower portion where the streamline for closely specified velocity increases and it vice versa. Figure 9.1b, it is clear that AR is greater than AQ or BQ is less than BR. The fluid is affiliated with passing from R to Q. This is associated with the change in the pressure in the fluid flow in the horizontal pipes. A steady flow is achieved at low flow speed beyond the limiting value called the critical speed. This flow loses steadiness and becomes turbulent. Once this when a fast moving stream encounters rock, a small foamy purple-like region called the white water rapids are formed. Figure 9 display of streamlines for some typical flow. For example, figure 9.8 describe a laminar flow where the velocity at different points in the fluid may have different magnitudes, but their direction are parallel. Figure 9.b gives a sketch of the turbulent flow. Some of turbulent flow fluid a jet line of striking a flat plate placed perpendicular to it. The figure example of the turbulent flow. नेक्स्ट है बर्नौली प्रिंसिपल। तो इसमें आता है कि फ्लूइड flow in a complex phenomena, but we can obtain some useful property for the study of the streamline flow using the conservation of energy. Consider a fluid moving in the pipe of the varying cross-sectional area. Let the pipe be at varying height as shown in figure 9.9. We now suppose that an incompressible fluid is flowing through the pipe in a steady flow. Its velocity must change as the consequence of the equation of the continuity. A force is required to produce this acceleration, which is caused by the fluid surrounding it. The pressure must be different in a different region. Bernoulli equation is a general expression that relates the pressure difference between the 2 points in a pipe to both velocity change, kinetic energy change, and the elevation height change, potential energy change. Take a developed relationship in the 2038. Consider the flow at the two regions 1 BC and the 2 D. Consider the fluid initially lying between the B and D in an infinitesimal time interval delta t. This fluid would have moved. Suppose v1 is the speed at the B and v2 is at d2 at d. Then fluid initially at B has moved a distance b1 delta t to C. b1 delta t is small enough to assume the constant cross section along the BC. In the same interval delta t, the fluid initially at D moves V along a distance equal to v2 delta t. Pressure P1 and P2 act as shown on the plane face of the area A1 and A2 binding the two regions. The work done on the fluid at left in BC is W1 is equal to P1 A1, B1 delta T is equal to P1 delta B. Since the same amount delta B passes through the both regions from the equations of continuity, the work done by the fluid at the other end D is equal to W2 is equal to P2 V2 V2 P2 A2 B2 delta T and P2 delta B, or the work done on the fluid is minus P2 delta V. For the work done on the fluid is W1 minus W2 is equal to P1 minus P2 delta V. Part of this work goes into changing the kinetic energy of the fluid and part goes into changing the gravitational potential energy. If the density of the fluid is rho and delta m, rho A1 B1 delta T and is equal to rho delta V is the mass passing through the pipe in the time delta T, then the change in the gravitational potential energy delta U is equal to rho G delta V H2 minus H1. The change in the kinetic energy is delta K is equal to half rho delta B V2 minus V2 K square minus B1 K square. We can apply the work energy theorem chapter 6 to this volume of the fluid and yields P1 minus P2 delta B is equal to half rho B V2 K square minus B1 K square plus rho G delta B H2 minus H1. We now divide each term by the delta V to obtain P1 minus P2 is equal to half rho V2 K square minus B1 K square plus rho G H2 minus H1. We can rearrange the term to obtain P1 plus half rho B1 K square plus rho G H1 equal to P2 plus half rho B2 K square plus rho G2. This is the Bernoulli equation. Since 1 and 2 refer to any two locations along the pipeline, we may write the expression as P plus half rho B plus half rho B square plus rho G equal to constant. The flow of an ideal fluid in a pipe of the varying cross section. The fluid in the cross section of the length B1 delta T moves to the section of the length B2 delta T in the time delta T. फिर यहाँ पर दिया हुआ है In other words, the Bernoulli relation may be stated as follows. As you move along a streamline, the sum of the pressure P, the kinetic energy per unit volume, rho B square by 2, and the potential energy per unit volume, rho GH, remains constant. Note that in applying the energy conservation principle, there is an assumption that no energy is lost due to friction, but in fact, when fluids flow, some energy does get lost due to the internal friction. This arises due to the fact that in a fluid flow, the different layers of the fluid flow with different velocity. These layers exert frictional force on each other, resulting in a loss of the energy. This property of the fluid is called the viscosity. And is discussed in in more detail in the later section. The lost kinetic energy of the fluid gets converted into the heat energy. Thus, the Bernoulli equation ideally applied to the fluid with zero viscosity on a non-viscous fluid. Another restriction on application of the Bernoulli theorem is that the fluid must be incompressible. The elastic energy of the fluid is also not taken into consideration. In practice, it has a large number of the useful applications and can help explain the wide variety of the phenomena for the low viscosity incompressible fluid. Bernoulli equation also does not hold for none of steady or the turbulent flow, because in that situation velocity and the pressure are constantly fluctuating in the time. When a fluid is at rest, that means velocity is 0 everywhere. Bernoulli equation becomes P1 plus rho g h1 is equal to P2 plus rho g h2. The P1 minus P2 is equal to rho g h1 2 minus h1, which is same as the equation 9.6. फिर आता speed of the flux or the Torricelli law. So the word flux, efflux means fluid outflow. Torricelli discovered that the speed of the efflux from an open tank is given by a formula identical to that at a freely flowing body. Consider a tank containing a liquid of density rho with a small hole in the side at a height by 1 from the bottom. The air above the liquid whose surface is at a height by 2 at pressure P. From the equation of the continuity we have B1 A1 is equal to B2 A2, so B2 is equal to A1 by A2 into B1. फिर यहाँ से आता है दिया हुआ Torricelli law. The speed of the flux V1 from the side of the container is given by the applications of the Bernoulli equation. If the container is open, then the top of the atmosphere is V1 is equal to root over 2gh. फिर आता है if the cross section area of the tank A2 is much larger than that of the hole, A2 is much greater than A1, then we may take the fluid to be approximately at the rest at the top, yani V2 is equal to 0. Now applying the Bernoulli equation at the point 1 and 2, and noting that at the hole P1 is equal to PA, the atmospheric pressure we have P1 PA plus half rho B1 के square plus rho G by 1 is equal to P plus rho G by 2. Taking by 2 minus by 1 is equal to H, we have B1 is equal to root over 2GH plus 2 rho minus rho A, 2P minus rho A by rho. When P is much greater than P and 2GH may be ignored, the speed of the flux is determined by the container pressure, which often occurs in the rocket propulsion. On the other hand, if the tank is open to the atmosphere, then the P is equal to PA and V1 is equal to root over 2GH. This is also the speed of the freely falling body. Equation 9.15 repeated Torricelli law. फिर आता है dynamic lift. So dynamic lift is the force that acts on the body, such as the airplane wing, a hydrofoil or a spinning ball by virtue of its motion through the fluid. In many games such as the cricket, tennis, baseball or the golf, we notice that the spinning ball deviates from its parabolic trajectory as it moves through the air. This deviation can be partially explained on the basis of the Bernoulli principle. Ball moving without a spin, to show that the streamline surround a non-spinning ball moving relative to the fluid. From the symmetry of the streamline, it is clear that the velocity of the fluid air above and below the ball at the corresponding point is the same, resulting in the zero pressure difference. The air therefore exerts no upward or the downward forces on the ball. Whereas the ball moving with the spin, the ball which is spinning drags air along with it. If the surface is rough, more air will be dragged. Figure 9.11b shows the streamlines of the air for a ball which is moving and spinning at the same time. The ball is moving forward and relative to it, the air is moving backwards. Therefore, the velocity of the air above the ball relative to the ball is larger and below it is smaller. The streamline get crowded above and rarefied below. फिर आता है कि this difference in the velocity of the air results in the pressure difference between the lower and the upper face, and there is a net upward force on the ball. This dynamic lift to the spinning is called as the Magnus effect. फिर आता है aerofoil or the lift on the aircraft wing. तो figure 9.11 C4 an aerofoil which is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through the air. The cross section of the wings of an aeroplane looks somewhat like the aerofoil shown in the figure 9.11 C with the streamline around it. When the aerofoil moves against the wind, the orientation of the wing relative to the flow direction cause the streamlines to crowd together above the wing more than those below it. The flow speed on the top is higher than that below it. There is an upward force resulting in a dynamic lift of the wings, and this balances the weight of the balance. The following example illustrates this. तो यहाँ पर दिया हुआ है फ्लूइड, यहाँ पर दिया क्या, यहाँ पर दिया है फ्लूइड स्ट्रीमिंग पास्ट ए स्टैटिक स्फीयर. फिर यहाँ पर दिया हुआ स्ट्रीम लाइन फॉर ए फ्लूइड अराउंड ए स्फीयर स्पिनिंग क्लॉकवाइज. यहाँ पर दिया हुआ है एयर फ्लोइंग पास्ट एन एरो फॉयल का है जो दिए हुए. फिर आता है अगला क्वेश्चन है कि ए बॉल A fully loaded Boeing aircraft has a mass of 3.3 × 10⁵ kg if its total wing area is 500 meters square. It is in level flight with a speed of 40 km per hour. Estimate the pressure difference between the lower and the upper surface of the wing. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. The density of the air is rho, यानी 1.2 kg per meter cube. तो इसमें आता है कि द वेट ऑफ द बोइंग एयरक्राफ्ट इज बैलेंस बाय द अपवार्ड फोर्स ड्यू टू द प्रेफर डिफरेंस. तो डेल्टा पी इक्वल टू ए इज इक्वल टू 3.3 × 10⁵ kg × 9.8. तो डेल्टा पी इक्वल टू 3.3 × 10⁵ kg × 9.8 बाय 500 मीटर स्क्वायर. तो 6.5 × 10⁻³ न्यूटन मीटर स्क्वायर. We ignore the small height differences between the top and the bottom sides. The pressure difference between them is delta P equal to rho by 2 V2 square minus V1 square, where V2 is the speed of the air over the upper surface and V1 is the speed of the of speed under the bottom surface. So v2 minus v1 is equal to 2 delta p by rho v2 plus v1. Taking the average of speed, b average equal to v2 by plus v1 by 2 यानी 960 किलोमीटर पर आवर यानी 264 मीटर पर सेकंड. तो b है v2 by minus v1 by b average equal to delta p by rho v average equal to 0.08. The speed of the beam needs to be only 8% higher than that below. अगला को है टॉपिक viscosity. तो most of the fluid are not identical ones and offer some resistance to the motion. The resistance to the fluid motion is like an internal friction analogous to the friction when the fluid moves on the surface. It is called the viscosity. This force is used when there is a relative motion between the layers of the liquid. Suppose we consider a fluid like the oil included between the two glass plates as shown in the figure 9.12. The bottom plate is fixed while the top plate is moved with a constant velocity v relative to the fixed plate. If the oil is placed by the honey, a greater force is required to move the plate with the same velocity. Hence, we say that the honey is more viscous than the oil. The same fluid in the contact with the surface has the same velocity that at the surface. Hence, the layer on the liquid in contact with the top surface moves with the velocity v, and the layer on the liquid in the contact with the fixed surface is stationary. The velocity of the layer increases uniformly from the bottom zero velocity to the top layer which velocity v. For any layer of the liquid, its upper layer pulls it forward while the lower layer pulls it backward. This results in the force between the two layers. This type of the flow is known as the laminar. The layers of the liquid slide over one another as the pages of a book do when it is placed flat on the table and the horizontal force is applied on the top cover. When the fluid is flowing in a pipe or a tube, then the velocity of the fluid liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the ball where it becomes zero. Figure 9.12b, the velocity of on a cylindrical surface in a tube is constant है जो दिखाया हुआ है. तो यहाँ पर a layer of the liquid sandwiched between the two parallel glass plates in which the lower plate is fixed and the upper one is moving to the right with velocity v. Velocity distribution for the viscous fluid in the pipe है जो दिखाए हुए. On account of this motion, a portion of the liquid which at some instant has the shape ABCD take the shape AEFD after short interval of the time delta t. During this time interval, the liquid has undergone a shear of strain delta x by L. Since the strain in a flowing fluid decreases with time continuously, unlike a solid, here the stress is found experimentally to depend on the rate of the change of the strain or the strain rate, that means delta x by L delta t for the v by L instead of the strain itself. The coefficient of the viscosity pronounced eta for a liquid for a fluid is defined as the ratio of the shearing of stress to the shearing of strain. तो eta equal to f by a v by L. तो f L v a होता है. The SI unit of the viscosity Pauli. Its further unit are the Newton second meter per meter square or Pascal per second. The dimensions of the viscosity are the m L minus 1 t minus 1. Generally, thin liquids like the water, alcohol, etc. are less viscous than the thick liquids like the coal tar, blood, glycerin, etc. The coefficient of the viscosity for some common fluids are listed in table 9.2. We point out two facts about the blood and the water that you may find interesting. As the table 9.2 indicates, blood is thicker, more viscous than the water. Further, the relative density N by N water of the blood remains constant between 0 degree Celsius and the 70 degree Celsius. तो यहाँ पर दिया फिल्म, यहाँ पर दिया 0.01 kg. तो मेजरमेंट ऑफ द कोफिशिएंट ऑफ द विस्कोसिटी ऑफ ए लिक्विड है जो दिखाया हुआ है. द विस्कोसिटी ऑफ द लिक्विड डिक्रीजेज विद द टेम्परेचर व्हाइल इट इंक्रीजेज इन द केस ऑफ द गैसेज. अब यहाँ पर है कि ए मेटल block of the area 0.1 meter square is connected to a 0.01 kg mass by a string that passes over an ideal pulley. A liquid with a film thickness of 0.3 mm is placed between blocks on the table. When the relay, the block moves to the right with a constant speed of 0.085 meter per second. To find the coefficient of the viscosity of the liquid, तो यहाँ पर आता है कि द मेटल ब्लॉक, यहाँ पर कहता है कि द मेटल ब्लॉक मूव्स टू द राइट बिकॉज ऑफ द टेंशन इन द स्ट्रिंग. द टेंशन T is equal to the magnitude of the weight of the suspended mass m. Thus the shear force F is equal to T is equal to mg equal to 0.01 गुना 9.8 यानी 9.8 गुना 10⁻² न्यूटन. Shear stress in the fluid F by A equal to 9.8 गुना 10⁻² by 0.1 न्यूटन per meter square. Strain rate is equal to V by L. तो H is equal to stress by strain rate, तो आएगा 3.4 गुना 10⁻³ पास्कल सेकंड. फिर आता है स्टोक्स लॉ. तो व्हेन अ बॉडी फॉल्स थ्रू अ फ्लूइड इट ड्राइव्स द लेयर ऑफ द फ्लूइड इन कॉन्टैक्ट विथ इट. A relative motion between the different layer of the fluid is felt and a real the body experiences a retarding force. Falling of a raindrop and swinging of a pendulum bob are some common examples of such motion. It is seen that the viscous force is proportional to the velocity of the object and the opposite to the directions of the motion. The other quantity on which the force F depends on the viscosity of the fluid and the radius of the sphere. ठीक है। उसके बाद कहता है कि क्लियरली विस्कस फोर्स ड्रैग फोर्स F इक्वल टू 6 pi eta A into V। तो दिस वी नोन एज द स्टोक्स लॉ। वी शैल नॉट derive the Stokes law. So this law is just an example of the retarding force which is proportional to the velocity. We can study its consequence on an object falling through a viscous medium. We consider a raindrop in the air. It affects initially due to the gravity. As the velocity increases, the retarding force also increases. Finally, when viscous force plus buoyant force becomes equal to the force due to gravity, the net force becomes zero, and so that the abbreviation. The sphere raindrop then the difference between constant velocity. Thus, in equilibrium, the terminal velocity Vt is given by 6 pi eta A Vt is equal to 4 pi by 3 A cube rho minus sigma into g, where rho and sigma are the mass density of the sphere and the fluid respectively. So Vt is equal to 2 A square rho minus sigma g by 9 eta आ जाता है. So the terminal velocity Vt depends upon the square of the radius of the sphere and inversely proportional to the viscosity of the medium. अब इसके बाद एक क्वेश्चन है कि the terminal velocity of a copper ball of radius 2 mm falling through the tank of the oil at 50 degrees Celsius is 6.5 cm per second. Compute the viscosity of the ball at 20 degrees Celsius. Density of the oil in 1.5 kg per meter cube and density of the copper is 8.9 kg per meter cube. तो भी है Vt इक्वल टू 6.5 minus 2 meter per second, यानी A इक्वल टू 2 minus 3 meter, G इक्वल टू 9.8 meter per second square, rho इक्वल टू 8.9 kg per meter cube. तो सिग्मा इक्वल टू 1.5 kg per meter cube. तो ईटा इक्वल टू 2/9 2 minus 3 का स्क्वायर बाई 9.8 बाई 6.5 minus 2, तो इसका गुना 6.4 3, तो कितना आ जाएगा 9.9 minus 1 kg per meter per second. फिर आता है सरफेस टेंशन. तो you must have noticed that oil and the butter do not mix. Butter baits you and me, but not ducks. Mercury does not bait glass, but butter sticks to it. Oil rises up the cotton bear in spite of the gravity. Sap and the water rises up to the top of the leaves of the tree. Hair of the paint brushes do not cling together when dry and even when dipped in butter, but from a fine tip when taken. इसका आगे कि all these and many more such experiences are related with the free surface of the liquid, as liquids have no definite shape but have a definite volume. They acquire a free surface when poured into a container. This surface possesses some additional energy. This phenomenon is known as the free surface tension and is consonant with only liquid, as gases do not have free surfaces. Let us now understand this phenomena. फिर आता है surface energy. The liquid stays together because of the attraction between the molecules. Consider a molecule built inside a liquid. The intermolecular distance is such that it is attracted to all the surrounding molecules. This attraction results in negative potential energy for the molecule, which depends upon the number and the distribution of the molecule around the chosen one. But the average potential energy of the molecule is same. This is supported by the fact that to take a collection of such molecules, the liquid, and to disperse them away from each other in order to evaporate or vaporize, the heat of the evaporation requires is quite large. For butter, it is of the order of 40 kilojoule per mole. Let us consider a molecule near the surface, figure 9.41b. Only lower half side of it is surrounded by the liquid molecules. There is some negative potential energy due to this, but obviously it is less than that of a molecule in the bulk, the only fully inside. Approximately it is half of the latter. Thus, molecule on a liquid surface have some extra energy in the comparison to the molecule in the interior. A liquid thus tends to have the least surface area which external condition permit. Increasing surface area requires energy. Most surface phenomena can be understood in the terms of this. What is the energy required for having a molecule at the surface? As mentioned above, roughly it is half the energy required to remove it entirely from the liquid. That means half the heat of the evaporation. फिर आता है कि finally what is surface? Since a liquid consists of the molecule moving about, there cannot be a perfectly sharp surface. The density of the liquid molecule drops rapidly to the zero around Z equal to 0 as we move along the direction indicated figure 9.1 c in a distance of the order of a few molecular phases. फिर आता है surface energy and the surface tension. So as we have discovered that an extra energy is associated with the surface of the liquid, the creation of more surface or spreading of the surface, keeping other things like the volume fixed requires a horizontal liquid film ending in bar free to the flat over the parallel guides. फिर यहाँ पर the stretching film, a film in the equilibrium or the film stretched an extra distance. अब यहाँ पर दिखाया हुआ है schematic. यहाँ पर क्या दिखाया हुआ है? यहाँ पर दिखाया हुआ है schematic picture of the molecules in the liquid at the surface and the balance of the forces. Molecules inside a liquid forces on the molecule due to the other person. Directions of the arrow indicates attractions of the repulsion. Same for a molecule at the surface, balance of the attractive AI and the repulsive R forces. फिर आता है कि सपोज दैट वी मूव the bar by a small distance d(h1). Since the area of the surface increases, the system now has more energy. This means that some work has been done against an external force. Let this internal force be F. The work done by the applied force is F dot D and Fd. From the conservation of energy, this is stored as the additional energy in the film. If the surface energy of the film is F per unit area, the extra area is 2dl. A film has two sides and the liquid in the between. So there are two surfaces and the extra energy is F into 2dl is equal to Fd, or F is equal to Fd by 2dl यानी कि F by 12. This quantity F is the magnitude of the surface tension. It is equal to the surface energy per unit area of the liquid interface and also equal to the force per unit length exerted by the liquid fluid on the movable bar. फिर आता है कि so far we have talked about the surface of the one liquid. More generally, we need to consider the fluid surface in contact with other fluids or the solid surfaces. The surface energy in that case depends upon the material of both the sides of the surface. For example, if the molecule of the materials attract each other, if the molecules of the material attract each other, the surface energy is reduced, while if they repel each other, the surface energy increases. Thus, more appropriately, the surface energy is the energy of the interface between the two materials and depends on both of them. फिर आता है कि we make the following observation from the above. Surface tension is a force per unit length or the surface energy per unit area acting in the plane of the interface between the plane of the liquid and any other substance. It also is the extra energy that the force of at the interface has as compared to the molecule in the interior. At any point on the interface besides the boundary, we can draw a line and imagine equal and opposite surface tension forces F per unit length of the line acting perpendicular to the line in the plane of the interface. The line is in the equilibrium. To be more specific, imagine a line of the atom for the molecule at the surface. The atoms to the left pull the line towards them, those to the right pull it towards them. This line of the atoms is in equilibrium under tension. If the line recall really marks the end of the interface as in figure 9.1 for A and B, there is only the force per F per unit length acting inwards. फिर आता है कि table 9.3 gives the surface tension of the various liquid. The value of the surface tension depends on the temperature. Like viscosity, the surface tension of the liquid usually falls with the temperature. तो यहाँ पर the surface tension of some liquid at the temperature indicated with the heat of the vaporization है जो दिखाया हुआ है. फिर आता है कि fluid will stick to a solid surface if the surface energy between the fluid and the solid is smaller than the sum of the surface energy between the solid air and the fluid air. Now there is attraction between the solid surface and the fluid liquid. It can be directly measured experimentally and schematically, shown in the figure 9.16. A flat vertical glass plate below which a vessel of the some liquid is kept forms one arm of the balance. The plate is balanced by the weight on the other side with its horizontal edge just overheated. The vessel is raised slightly till the liquid just touches the glass plate and pulls it down a little because of the surface tension. Weight are added till the plate just clears the water. फिर आता है कि suppose the additional weight required is W. Then from the equation 9.20, the discussion given there, the surface tension of the liquid air interface is ml minus 1 t minus 2 ml minus 1 और t minus 2 होता है फिर पास्कल 180 में इक्वल टू होता है 1.013 गुना 3 10 को 5 पास्कल और स्केलर है। डेंसिटी का होता है रो ml minus 3 और भी स्केलर है। स्पेसिफिक ग्रेविटी का कोई डायमेंशन नहीं है, डायमेंशन लेस ही रो सब टाइम्स पर रो वाटर होता है, स्केलर है। कोफिशिएंट ऑफ विस्कोसिटी का ये था ईटा, तो इसका होता है ml minus 1 t minus 1 यूनिट है इसका पास्कल सेकंड और द पॉजिली और ये स्केलर क्वांटिटी है। सरफेस टेंशन का होता है एम टी माइनस 2 न्यूटन पर मीटर और ये भी क्या है स्केलर क्वांटिटी है। अब इसका देखेंगे कुछ सॉल्यूशन। तो जैसे एक्सप्लेन व्हाई द ब्लड प्रेशर इन ह्यूमन इज ग्रेटर देन एट फीट देन इन द ब्रेन। Atmospheric pressure at a height of about 6 km decreases to nearly half of its value at the sea level, though the height of the atmosphere is more than the 4 km. Hydrostatic pressure is scalar quantity even though pressure is force divided by the area। तो इसमें आता है कि the pressure of liquid is given by the definition P is equal to H rho g, where P is the pressure, H is the height of the liquid column, rho is the density of the liquid और g is the deflection due to gravity। तो इसमें कहता है कि it can be inferred that pressure is directly proportional to the height, hence the blood pressure in the human vessel depends on the height of the blood column in the body. The height of the blood column is more at the feet than it is at the brain, hence the blood pressure at the feet is more than it is at the brain। Density of air is the maximum near the sea level. Density of air decreases with increase in the height from the surface. At a height of about 6 km, density decreases to nearly half of its volume at the sea level. Atmospheric pressure is proportional to density, hence at a height of 6 km above the surface, it decreases to nearly half of its value at the sea level। When force is applied on a liquid, the pressure in the liquid is transmitted in all directions. Hence, hydrostatic pressure does not have a fixed direction and it is a scalar physical quantity। उसके बाद फिर आता है कि explain why the angle of the contact of the mercury with the glass is obtuse while that of the water with the glass is acute। और दूसरा है कि water on the clean glass surface tends to spread out while mercury on the surface tends to form drop। The put differentially water gets glass while the mercury does not। तो इसमें आता है कि the angle between the इसमें आता है कि the angle between the tangent to the liquid surface at the point of the contact and the surface inside the liquid is the angle of the contact theta as shown in the figure। तो ये मर्करी इन द ग्लास हो गया और ये वाटर ऑन द ग्लास हो गया। तो एफ एल एफ ए एंड एफ आर द रिस्पेक्टिव इंटरफेसियल टेंशन बिटवीन द लिक्विड एयर fluid air and the fluid liquid interface at the line of the contact। the surface force between the three media must be in equilibrium, that means cos theta is equal to FFA minus FD by FLA। The angle theta is obtuse if FFA is less than FLA as in the case of the mercury on the glass। This acute angle is FFLA is less than FLA as in the case of the water on the glass। Mercury molecules which make an acute angle with the glass have a strong force of the attraction between themselves and a big force of the attraction towards solid, hence they tend to form the drops। On the other hand, water molecules make acute angle with the glass, they have a big force of the attraction between themselves and a strong force of the attraction towards the solid, hence they tend to spread out। Surface tension is the force acting upon a length at the interface between the plane of a liquid and any other surface। This force is dependent on the area of the liquid surface, and surface tension is also independent of the area of the liquid surface। Water with the detergent dissolved in it has a small angle of contact. This is because for a small theta there is a fast capillary rise of the detergent in the cloth। The capillary rise of a liquid is directly proportional to the cosine of the angle of the theta। If theta is small, then the cos theta will large and the rise of the detergent in the water will in the cloth will fast। A liquid tends to acquire a minimum surface area because of the presence of the surface tension। The surface area of the sphere is the minimum for a given volume, hence under no external forces liquid drops always take the spherical shape। अगला क्वेश्चन है कि fill in the blanks using the words from the list appended with each statement। तो surface tension of the liquid generally, तो इसमें आता है कि the surface tension of a liquid is inversely proportional to temperature। तो most fluids of the resistance to their of motion, this is like internal mechanical friction known as the viscosity। Viscosity of gas will increase with temperature while viscosity of liquid decrease with temperature। फिर आता है with reference to the elastic modulus of the rigidity for the solid, the shearing force is proportional to the shear of strength। With reference to the elastic modulus of rigidity for the fluid, the shearing of force is proportional to the rate of the shear of strength। फिर आता है for a steady flowing fluid, an increase in the flow of speed at a constriction follow the conservation of the mass, a Bernoulli principle। For the model of a plane in a wind tunnel, turbulence occurs at a greater speed than it does for the actual plane। This follows from the Bernoulli principle and the different Reynolds number are associated with the motions of the two planes। इसके बाद फिर आता है to explain why to keep a piece of the paper horizontal you should blow over it not under it। When we try to close a tap with our finger, fast jet of the water goes through the opening between our finger, or the size of the needle of the fringe control flow rate better than the thumb pressure exerted by the doctor while administering an injection or a fluid Flowing out of the small hole in the vessel resulting in the backward thrust on the vessel. A spinning thick cricket ball in the air does not follow a parabolic trajectory. तो इसका आता है आंसर कि when air is blown under a paper, the velocity of air is greater than the paper, then it is above it. As Bernoulli principle, hydrospheric paper do so under the paper. This makes the paper fall. To keep a piece of the paper horizontal, one should blow over it. This increases the velocity of the air above the paper. As the Bernoulli principle of atmospheric pressure reduces the paper and the paper remains horizontal. According to the equations of the continuity, A area into velocity is equal to constant. For a smaller opening, the velocity of the flow of the fluid is greater than it is when the opening is bigger. When we try to close a tap of the water with our finger, fast jet of the water goes through the opening in between our finger. This is because very small openings are left for the water to flow out of the pipe. Hence, area and velocity are inversely proportional to each other. The small opening of the free needle controls the velocity of the blood flowing out. This is because of the equation of the continuity. At the constriction point of the fringe system, the flow rate suddenly increases to a high value of the constant thumb pressure applied. When a fluid out from a small hole in the vessel receives a backward thrust. A fluid flowing out from a small hole has a large velocity according to the equations of the continuity. तो एरिया इंटू velocity हो जाता है क्या कांस्टेंट. According to the law of the conservation of momentum, the vessel attains a backward velocity because there are no external forces acting on the system. और फिर आता है कि the spinning cricket ball has two simultaneous motion, rotatory and a linear. These two types of the motion oppose the effect of each other. This decreases the velocity of the air flowing below the ball. Hence, the pressure on the upper part of the ball becomes lesser than that on the lower part, and if bad force acts on the ball, therefore the ball takes a curved path. It does not allow a parabolic path. Next है कि 50 kg girl wearing high heels shoes balance on a high heel, single heel. The heel is circular with a diameter of 1 centimeter. What is the pressure exerted by the heel on the horizontal floor? The mass of the girl is equal to 50 kg. Diameter of the head is equal to 1 centimeter. Giant पर 1 meter. रेडियस ऑफ द हिल हो गया आर इक्वल डी बाई टू इक्वल टू 0.005 मीटर. एरिया ऑफ द हिल हो गया पाई आर स्क्वायर. तो 7.85 गुना 10⁻⁵. तो फोर्स एक्सर्टेड बाय द हिल ऑन द फ्लोर होगा एफ इक्वल टू एम जी यानी 50 गुना 9.8 यानी 490 न्यूटन. तो पी इक्वल टू एफ फोर्स पर एरिया तो 490 बाई 7.5 गुना 10⁻⁵ आएगा 6.24 गुना 10⁻⁶ न्यूटन पर मीटर स्क्वायर. Therefore, the pressure exerted by the hill on the horizontal floor is 6.24 गुना 10⁻⁶ न्यूटन पर मीटर स्क्वायर. अगला है टॉरिफिल बैरोमीटर. यूज मर्करी पास्कल डुप्लीकेटेड इट यूजिंग द ठीक है determine the height of the wind column for the normal atmospheric pressure. तो density of mercury ρ1 is equal to 13.6 गुना 10⁻³ kg per meter cube. height of the mercury column H1 is equal to 0.616. density of the जो दिया हुआ है वह 984 kg per meter cube. और height of the H2 हो जाएगा मान लेते हैं एक्सलेशन ड्यू टू ग्रेविटी G equal to 9.8. the pressure in both the columns is equal. the pressure in the mercury column is equal to pressure in the तो ρ1 H1 जी इक्वल टू ρ2 H2 जी. तो H2 इक्वल टू ρ1 H1 बाई ρ2. तो कितना आ जाएगा 10.5 मीटर. हेंस द कितना आ जाएगा कि इसका 10.5 मीटर आ जाएगा. नेक्स्ट है कि वर्टिकल ऑफशोर स्ट्रक्चर इज बिल्ट टू विथस्टैंड ए मैक्सिमम स्ट्रेस ऑफ 10 के पावर 9 पास्कल. इज द स्ट्रक्चर सुटेबल फॉर putting up on the top of an oil well in the ocean. Take the depth of the ocean to be roughly 3 km and ignore the ocean current. तो maximum allowable stress of the structure हो जाएगा P equal to 10⁻⁹ पास्कल. डेप्थ ऑफ द ओशन हो जाएगा 3 गुना 10⁻³ मीटर. और डेंसिटी ऑफ वाटर हो जाएगा 10⁻³ kg पर मीटर क्यूब. एक्सलेशन ड्यू ग्रेविटी G इक्वल टू 9.8 मीटर पर सेकंड स्क्वायर. D इक्वल टू रो डी जी. तो 2.94 गुना 10⁻⁷ पास्कल हो जाएगा. The maximum allowable stress for the structure 10⁻9 Pascal greater than the pressure of the sea water 2.94 गुना 10⁻⁷ Pascal. The pressure exerted by the ocean is less than the pressure that the structure can withstand. Hence the structure is suitable for putting upon the top of the oil well in the ocean. फिर आता है कि hydraulic automobile lift is designed to lift the cars with the maximum mass of the 3000 kg. The area of the cross section of the piston carrying the load is 425 centimeter square. The height maximum pressure would be smaller piston to have. The maximum area mass of the car that can be lifted is equal to 300 kg. Area of cross section was 425 centimeter square यानी 425 गुना 10⁻⁴ मीटर स्क्वायर. मैक्सिमम फोर्स एफ इक्वल टू एम जी हो गया यानी 29,400. तो मैक्सिमम फोर्स एक्सर्टेड ऑन द लोड कैरिंग एफ पी इक्वल टू एफ बाई ए. तो यहाँ से निकालेंगे तो कितना आ रहा है 6.91 पास्कल. तो प्रेशर ट्रांसमिटेड इक्वली इन ऑल डायरेक्शन इन लिक्विड. देयरफॉर द मैक्सिमम प्रेशर दैट द स्मॉलर पिस्टन वुड हैव इज 6.91 पास्कल. अगला सवाल ए यू ट्यूब कंटेन्स वाटर एंड methylated spirit separated by the mercury. The mercury columns in the two arms are in the level with 10 cm of the water in one arm and 12.5 cm of spirit in the other. So what is the specific gravity of the spirit? So the given system of water, mercury in the methylated spirit is shown in the figure. Height of the spirit column H1 is equal to 12.5 cm यानी 0.125 मीटर. Height of the water column is 2 equal to 10 centimeter 0.1 meter. So P naught is equal to atmospheric pressure, P1 is ρ1 is equal to density of spirit और A2 is equal to density of the water. तो यहाँ से निकालेंगे तो प्रेशर एट पॉइंट P is equal to ρ0 प्लस H1 ρ1 G, प्रेशर D is equal to P naught plus H2 ρ2 G. तो P naught plus H1 ρ1 G is equal to H2 ρ2 G. तो ρ1 by ρ2 हो जाएगा H2 by H1 यानी 0.8. Therefore the specific gravity of the fluid कितना हो जाएगा 0.8. नेक्स्ट है in the problem 10.9, if 15 centimeter of water and spirit each are further poured into the respective arms of the tube, but a difference in the level of the mercury in the two arms of specific gravity of mercury 13.6 है. तो height of the water column H1 is equal to 25 centimeter, height of the spirit column 27.5 centimeter. Density of water ρ1 is equal to 1 gram per centimeter cube, density of spirit ρ2 is equal to 0.8 gram per centimeter cube, density of mercury 30.6 gram per centimeter cube. Let h be the difference between the levels of the mercury in the two arms, pressure exerted by the height h rho g हो जाएगा. तो h गुना 13.6. अब यहाँ से अगर निकालेंगे तो डिफरेंस बिटवीन द प्रेशर एक्सर्टेड बाय द वाटर एंड द स्पिरिट h1 ρ1 g माइनस h1 ρ1 g इज इक्वल टू 3 ग्राम. तो इक्वेशन 13.6 h g इज इक्वल टू 3 ग्राम. तो यहाँ से h कितना आएगा 0.0221 सेंटीमीटर. हेंस द डिफरेंस बिटवीन द लेवल्स ऑफ द मर्करी इज 0.221 सेंटीमीटर आ जाएगा. नेक्स्ट है कैन द बर्नौली इक्वेशन बी यूज्ड टू डिस्क्राइब द फ्लो ऑफ द वाटर थ्रू ए रैपिड in a river explain. तो Bernoulli equation cannot be used to describe the flow of the water through a rapid in a river because the turbulent flow of the water. This principle can only be applied to a streamline flow. फिर आता है does it matter if one use the gauge pressure instead of the absolute pressure in applying the Bernoulli equation? Explain. It does not matter if one use the gauge pressure instead of the absolute pressure while applying the Bernoulli equation. The 2 points where the Bernoulli equation is applied should have significantly different atmospheric pressure. अगला क्वेश्चन glycerin follows steadily through a oriented tube of length 1.5 meter and radius 10.0 centimeter. If the amount of the glycerin collected per second at 1 inch per guna the 1 of 3 kg per second, what is the pressure difference between the 2 ends of the tube? Density of the glycerin 1.3 guna the 13 kg per meter cube and viscosity of glycerin 0.83 pascal second दिया हुआ है. तो आता है कि लेंथ ये दिया हुआ है 9.8 गुना 10⁻2 पास्कल. लेंथ ऑफ द हॉरिजॉन्टल ट्यूब L is equal to 1.5 मीटर, रेडियस ऑफ द ट्यूब R is equal to 1 सेंटीमीटर यानी 0.01 मीटर, diameter of the tube D is equal to 2 R is equal to 0.02 मीटर, the glycerin of the flowing rate 4.0 गुना 10⁻³ kg per second और M is equal to 4.0 गुना 10⁻³ kg per second. तो डेंसिटी ऑफ ग्लिसरॉन हो जाएगा ρ is equal to 1.3 गुना 10⁻³ kg per meter cube, eta is equal to 0.083 pascal second. तो V is equal to M by ρ यानी 4 गुना 10⁻³ by 1.3 गुना 10⁻³ आ जाएगा यानी 3.08 गुना 10⁻6 मीटर क्यूब सेकंड. तो V इज इक्वल टू आएगा 8 पी आर के पावर 4 बाई 8 ईटा एल. तो P इज इक्वल टू 8 V8 ईटा एल यानी पाई आर के पावर 4. तो यहाँ से 9.8 गुना 10⁻2 पावर आ जाएगा. तो R इज इक्वल टू हो जाएगा 4 रो V बाई पाई डी ईटा. तो यहाँ पर आएगा 0.3. द रेनॉल्ड्स नंबर इज अबाउट 0.3. हेंस द फ्लो क्या हो जाएगा लैमिनार. Next hack in a test experiment on a model airplane in a wind tunnel, the flow of speed on the upper and the lower surface of the wing was 40 meter per second and 53 meter per second respectively. So what is the lift on the wing if the area is 2.5 meter per square? Take the density of air to be 1.3 kg per meter cube. So speed of the wind on the upper surface of the wing हो जाएगा 70 meter per second और speed of the wind on the lower surface of the wing हो जाएगा 53 meter per second. तो एरिया ऑफ द विंग हो जाएगा एज इक्वल टू 2.5 मीटर स्क्वायर और डेंसिटी ऑफ हो जाएगा 1.3 kg पर मीटर क्यूब. तो P1 प्लस हाफ रो V1 इक्वल टू P2 प्लस हाफ रो V2 के स्क्वायर. तो P2 माइनस P1 इक्वल टू हाफ रो V1 के स्क्वायर माइनस P2 के स्क्वायर. तो लिफ्ट ऑफ यहाँ से करेंगे तो P1 is the pressure on the upper surface of the wing, P2 is the pressure on the lower surface of the wing. The pressure difference between the upper and the lower surface of the wing provide lift to the airplane. The lift on the wing हो जाएगा P2 minus P1 into A. तो हाफ रो V1 के स्क्वायर माइनस V2 के स्क्वायर into A. तो आ जाएगा 1.51 गुना 10⁻³ न्यूटन. Therefore the lift on the wing of the plane आएगा 1.51 गुना 10⁻³ न्यूटन. नेक्स्ट है कि फिगर 10.23 A and B refer to the steady flow of a non-viscous fluid. Which one of the following is the incorrect और why? तो यहाँ पर जो टेक द केस फॉर द फिगर B. A1 है एरिया ऑफ द पाइप 1, A2 एरिया ऑफ द पाइप 2, B1 स्पीड ऑफ द लिक्विड इन द पाइप 1, B2 स्पीड ऑफ लिक्विड इन द पाइप 2. तो A1 B1 इक्वल टू A2 B2. उसके बाद फिर कहता है कि when the area of the cross section in the middle of the venturimeter is small, the speed of the flow of the liquid through this part is more. According to the Bernoulli principle, if the speed is more, then the pressure is less. Pressure is directly proportional to the height, hence the level of the body of the pipe is 2 is less. Therefore the figure 2 है जो A है जो पॉसिबल नहीं है. Next question कि the cylindrical tube of a spray pump has a cross section of the 8 cm square and one end of which has a 40 fine holes each of diameter 1 mm. If the liquid flow inside the tube is 1.5 meter per minute, what is the speed of the ejection of the liquid through the hole? The area of the cross section of the spray pump A1 is equal to 8 cm square यानी 8 meter square. Number of holes N is equal to 40. Diameter of the each hole D is equal to 1 mm and 1 3 meter. रेडियस ऑफ इच होल r इक्वल टू d/2 यानी 0.5 × 10⁻⁻10। तो एरिया ऑफ द क्रॉस सेक्शन ऑफ इच होल होगा a इक्वल टू पाई r स्क्वायर। तो टोटल एरिया ऑफ 40 होल्स हो जाएगा A2 इज इक्वल टू n इंटू ए, तो आएगा 31.41 × 6 मीटर स्क्वायर। नेक्स्ट है स्पीड ऑफ द फ्लो ऑफ द लिक्विड इन द ट्यूब हो जाएगा v1 इज इक्वल टू 1.5 मीटर पर मिनट यानी 0.025 मीटर पर सेकंड। स्पीड ऑफ द रिएक्शन ऑफ द लिक्विड थ्रू द होल हो जाएगा v2 A1 v1 इज इक्वल टू A2 v2, तो v2 इज इक्वल टू 1 v1 बाई A2 यानी 0.633 मीटर पर सेकंड। फॉर द स्पीड ऑफ द रिएक्शन ऑफ द लिक्विड थ्रू द होल हो जाएगा 0.633 मीटर पर सेकंड। अगला सवाल है ये यूज सेफ्ट बार डिपेंड इन द सोप सॉल्यूशन एंड रूम बेड द थिन सोप फिल्म formed between the bar and the light slider supports a weight of 1.5 × 2 Newton, which includes the small weight of the slider. The length of the slider is 30 cm. What is the surface tension of the film? So the weight that the soap film support W equal to 1.5 × 2 Newton. Length of the slider is equal to 0.3 meter. A soap film has two surface. Total length 12 is equal to 0.6 meter हो जाएगा। तो F equal to force by of weight by 12 यानी 2.5 × 2 Newton per meter. Therefore the surface tension in the film is 2.5 × 2 Newton per meter. अगला सवाल फिगर 10.2 for a thin liquid film supporting a small weight 4.5 × 2 Newton. What is the weight supported by a film on the liquid surface at a temperature in the figure B and explain your answer physically. तो the length of the liquid film supported by the weight L is equal to 40 cm यानी 0.4 cm. The weight supported by the film W is equal to 4.5 × 2 Newton. तो liquid film two surface tension W by 2L, तो 4.5 × 2 by 2.0 2 0.4 यानी आएगा 5.625 × 2 Newton meter. So in all the three cases, the liquid is the same, temperature is also the same for each case, hence the surface tension in the figure B and C is the same, and that 5.625 × 2 Newton per meter. Hence, the length of the film on the case is 40 cm, the bed support in the case is 4.25 × 2 Newton. Next है कि what is the preference for the drop of mercury radius 3 mm at the room temperature, surface tension of the mercury and at that temperature 20 degrees Celsius 4.65 × 1 Newton per meter. The atmospheric pressure 1.01 × 5 Pascal. Also give the pressure inside the drop. So 1.01 × 5 Pascal is 10 Pascal. Radius of the mercury drop R equal to 3 mm and 10 × 3 meter, or radius surface tension of mercury F equal to 4.65 × 1 Newton per meter. The atmospheric pressure ρ0 equal to 1.01 × 5 Pascal. Total pressure inside the mercury drop FF pressure inside mercury plus atmospheric pressure यानी 2s/r plus p0, तो आएगा 1.01 × 5 पास्कल। तो एक्सेस प्रेशर आएगा 2s/r यानी 310 पास्कल। इसका आंसर आ जाएगा कैलकुलेट करने पर। अगला सवाल व्हाट इज द एक्सेस pressure inside the bubble of the soap solution of radius 5 mm given that the surface tension of the soap solution at the temperature 20 degrees Celsius is 2.5 × 2 Newton per meter. If an air bubble of the same dimensions were formed at a depth of the 40 cm inside the container containing the soap solution of the radius 51.2, what would the pressure inside the bubble? Air atmospheric pressure 1.01 × 5 Pascal. The excess pressure inside the soap bubble is 20 Pascal. Pressure inside the air bubble 1.06 × 5 Pascal. The soap bubble of the radius r equal to 5 mm यानी 5 × 3 meter. Surface tension of soap solution F equal to 1.5 × 2 Newton per meter. यहाँ से निकालना तो relative density of soap solution 1.2, density of the soap solution rho equal to 1.2 × 4/3 kg per meter cube. Air bubble formed at depth h equal to 40 cm यानी 4 meter, और r equal to 5 mm यानी 5 × 3 meter. तो 1 atmospheric pressure equal to 1.01 × 5 Pascal, और reflection degree gravity is equal to 9.8 meter per second square. P is equal to 4/r यानी 20 Pascal. Therefore, the excess pressure for the soap bubble is 20 Pascal. The excess pressure for the air bubble given by the different period F equal to 2s/r and 10 Pascal. Therefore, the excess pressure for the air bubble is 10 Pascal at the depth of the 0.4 meter. The total pressure for the air bubble is atmospheric pressure plus H rho g plus P dash यानी 1.06 × 5 Pascal. तो इसका है जो आंसर आ जाएगा। तो यहाँ पर है जो चैप्टर कंप्लीट होता है। सही है।